So this segment of Technical Forum is part one in a series about unintuitive electrical hazards. And today we're going to be talking about induction. Has everyone had a chance to use the Slido link? Okay, so I'll start with some brief definitions just so we're all on the same page. A hot stick, that's in red there. That's what a hot stick looks like. And portable earths, that's the yellow cables with the metal clamps on the end. So the portable earths are used in high voltage isolation and access to prevent dangerous voltages. And when the worker attaches the portable earths, they use a hot stick for that process. And the hot stick's important because it allows the worker to remain at a safe distance when they're doing that. And the hot stick's fully insulated. It's also called an earthing stick because it's used for earthing. And this is important in case there's a voltage on the circuit conductor. And that's one scenario where a worker might need to apply some earths, a couple of transmission lines. And when the worker goes to apply the earths, they're expecting that there's no voltage on the circuit conductors at that point, but sometimes there might be. So one reason for that could be the operator might have made a mistake in their isolation. That could lead to dangerous voltages on the circuit conductors, but there are other reasons too, which we're going to look at. So here's a scenario to get us thinking about these hazards. So imagine that you're a lines person and you need to remove a set of earths from an overhead line. And then you realise that you haven't brought your insulated hot stick for this purpose. So it raises a question in your mind, which is, why is it so important that you use the hot stick when you're removing the earths? And we're going to look at the theory behind answering that question for the rest of this session. Here's quiz one. Okay, so a linesman's about to remove the last set of earths from an overhead line. There's a parallel transmission line next to it that's in service, and if he accidentally touches the line a moment before he removes the last earth, then he'll receive a shock from the isolated line. So the question is, which circuit elements best represent where the energy comes from? This is select one or more. Is it A, the lines are like a capacitor? B, the lines are like a transformer? C, the lines are like a battery? Or D, the linesman's like a Van de Graaff generator? So I'll give you a minute. And if you don't know, just guess because the answers are anonymous. So just put in a guess anyway. No one will know who it was. All good? I'll move on to quiz two.
About quizzes. Whew.
Quiz two. A linesman's about to connect a set of earths to an overhead line and it's already earthed at the remote end, a few kilometres away. And there's another parallel transmission line that's still in service. And if the linesman accidentally touches the line a moment before he applies the last earth, he'll receive a shock. So again, the question is, which circuit elements best illustrate where the energy comes from that shock? The options are the same again, select one or more.
I think I've misinterpreted the last question.
So you picked up the difference between quiz two and quiz one questions?
Well, no, I clearly didn't read quiz one enough.
Ah, okay.
No, quiz one was isolated and it was de-isolating, whereas this one is isolating it, right?
Yes.
On in this remote end.
Yeah, the earth at the remote end is the key difference. Yeah, I'll give you a minute. Actually, this is the last quiz. It's only 2 questions today.
That's good.
Okay.
We
Okay.
when we are educated.
So
No way.
let's see if we can show the results. So, okay, in quiz one, the most popular, some of this is obscured on my screen. No one said the lines are like a battery. The most popular one in quiz 1, the popular answer was that the lines are like a transformer. And quiz 2, the most popular answer was that the lines are like a capacitor. No one said it was like a battery, and I think no one said it was like a Van de Graaff generator. Oh, there we go. Okay, we're going to look at some theory, and then we'll come back to these. I won't keep you in suspense for very long. Okay, so let's think about a couple of capacitors in series. And then let's merge them. Now we have one capacitor, but we have an extra plate in the middle. And let's apply 100 volts across our capacitor, across the outer plates. And then we need to think about, let's say, what the voltage is from the plate on the left, the plate in the middle. And you can probably tell just by looking at it, you can probably guess, but we'll go through the theory behind figuring out the voltage. So the outer plates set up an electric field, which is marked in those grey arrows there. And then with the electric field, we have an electric potential in the space between the plates. And that's the plot on the bottom right. That's the electric potential. And we know that the difference in the electric potential between the rightmost plate and the leftmost plate, that's 100 volts, because that potential difference is what we mean when we say the voltage is 100 volts. And between these plates, the electric potential varies across space as a straight line. So that's the plot on the bottom right. And the relationship between the electric field and the electric potential here is that the electric field is the gradient of the electric potential, and it points down the hill. And this middle plate in our capacitor is halfway up the hill. And so that means that the voltage from the left-hand plate to the middle plate is 50 volts. This is the electric field of a charged wire. And we can also look at the electric potential that it sets up as a heat map. So here, the live wire is on the top left, and there's an isolated wire on the top right, and then an earth plane on the bottom. So the arrows represent the electric field, and then the colours represent the electric potential. So the highest potential is at the live wire in purple, and lowest potential at the earth in blue. And then the isolated wire is a bit like the middle plate of our capacitor that we looked at earlier. Now, it's not exactly like it because it's not directly in between the live wire and the earth plane, but it is in the electric field set up by the live wire. And this means that the potential of the isolated wire is also affected by the live wire. And you can see that from the color on the heat map where the isolated wire is. It's in a different color compared to the earth down the bottom. So that means that there's a voltage from the isolated wire to earth. And the voltage from the isolated wire to earth is caused by the live wire. And there's something similar going on with our transmission lines. So here are our transmission lines. Often the distance are the towers, and then we've taken a cross-sectional cut of the conductors, simplifying it as one conductor per phase. And on the left, we have the energized line, and on the right, we have the isolated line. And at this moment in time, the rightmost conductor on the energized line is at the highest potential. And you can see the heat map shows how this affects the potential of each conductor on the isolated line. And then the earth is down the bottom where that shade of green represents 0 volts. So it turns out that because the live line on the left is actually operating at 500 kV, in this case, our simple model gives an RMS voltage of 67 kV for that conductor nearest on the isolated line. And the same effect is affecting all 3 conductors. So that conductor it's like a bit like the middle plate of the capacitor again. The geometry is a little bit different, but the principle is the same. Now, we can make a model, and we're just going to look at one conductor from each line for our model, just to keep it simple. And that's those two there that I've marked on the drawing. And the model looks like this. So this is like the two capacitors that we started with. So that node on the left is the, let's say, the blue phase from the live line, and the node on the right is the red phase from the isolated line, and there is a capacitance between them. And then there's also a capacitance to Earth. And so, because the live line is energized, what we get is a capacitive voltage divider. And so that voltage divider determines the voltage on the isolated phase conductor, same for all three of the isolated phase conductors. And this is the same phenomenon we're looking at in that last diagram, just represented a different way. And it's worth noticing that the induced voltage here actually does not depend on the length of the line. It can actually occur in much shorter conductors. And because of these capacitances, we have a capacitive charging current flowing. And that means that if a worker touches the isolated conductor, then the charging current will flow through the worker. Now that charging current, it's present whether or not the live line is loaded. Even if the live line is just energized, but there's no load at the end, you'll still get this effect where if a worker touches it, charging current will flow through the worker. And so the worker is represented by these resistors on the right here. And this has been studied in the field, actually. So some researchers in America looked at two transmission lines in parallel. There was a live line operating at 115 kV, and then there was an isolated line next to it. And they just connected a 1,000 ohm resistor from the isolated line to Earth, and that represents a worker. And then they measured the current through the 1,000 ohm resistor on the isolated line. What they found was that 740 milliamps flowed. So to put that in perspective, so that represents the shock current through the worker. To put that in perspective, an RCD will trip at 30 milliamps to prevent a fatality if there's a shock. This is 740 milliamps, so it's definitely hazardous. So this is the correct answer to quiz number 1. The correct answer is A, the lines are like a capacitor. Now that scenario that we talked about at the beginning where I was saying, imagine you're a linesman and you've left your hot stick behind and you need to remove some earths. That's based on a real incident. It occurred in Queensland in 2009. And the worker, he didn't use the hot stick when he was removing the earths and he died. And there's an entire coroner's inquest report about it that I've included in the references. It even has some photos showing exactly what he did wrong. And he did not use the hot stick. So if you're connecting or removing earths, stay at a safe distance, use the hot stick. And if you need to access circuit conductors, just make sure that they're earthed on either side of the work site. And
Sorry, Edward, a couple of questions there about work earths and working inside them. And others might be able to answer the question. We would normally expect a person to be able to see both ends of that, if it's a work earth, to be able to work within it, or do we accept the remote end and that type of stuff?
Yes, I will be covering that in part 2. So the working earths need to be within line of sight. The permit earths that you put at the remote ends of the line are not adequate to manage the hazard in this case, and the reasons why they're not adequate we'll talk about in part 2. Address this question. Yeah, I'm glad that you raised that. Okay, so that's the most important thing that we'll talk about in part 2, actually. So terms for this phenomenon, Simplest name for it is just capacitor effect. And if you want to be a little bit more precise, you could just say electric field induction. And then the other term you might see is electrostatic induction. So we're going to talk about the quiz 2 scenario in part 2 very shortly. And I'll just show you my references. So reference number 3 there, that's the coroner's inquest report. So it shows exactly what that worker did wrong in Queensland that led to his death. And then reference number 5, there's an IEEE paper. So if you want to read about the technical details of this phenomenon in more detail, like, for example, Darcy's point about modelling it correctly, then there's more detail in the IEEE paper. Okay, we are on schedule, and we've got some time for if there are any more questions or discussion points, we've got some time for that, and then we'll need a brief break before part 2 because it's a bit longer and more complicated. Is there anything you'd like me to go back over?
With the diagram you brought up showing the capacitors in circuit and then the resistors across that second capacitor representing the lineman, could you bring that slide up again for a second?
Okay. Is that this one?
Yes, thank you. In the scenario where they've used the hot stick to get the lines on, obviously, and then you've got that other side of that capacitor on the vertical there, which is next to the shock current. That capacitor is not there when the red phase is earthed, or it is there because it's too far away, that earthing.
When you earth the circuit conductors at the work area, so that your working earths are within line of sight from when you're working, in that case, it does, yes, it shorts out the capacitor that you can see there from the isolated conductor to earth. Now,
I guess my question was, in that scenario where you do have an effective local earth, is there still as much risk removing, I'm not saying do it, but how much risk is there not using the hot stick and removing the earth by hand? How fast does the voltage and current effectively build up? And would it be quick enough that you'd remove it safely, but then a fraction of a second later, it's going to arc to you and then give you the shock current anyway?
Hey, Mark, I'm glad that you raised this. I actually will address, I've got this exact point in the part 2 content, so okay. It's very important. With this phenomenon, the voltage appears instantly. So that's why the worker died in Queensland in 2009. It's because as soon as you remove the earths, that capacitive voltage divider effect creates a hazardous voltage, thousands of volts instantly. That addresses your question?
Yes, but how much charge is moving, I guess, but it is relevant, obviously. So, I mean, it is still dangerous, yeah.
So one way of thinking about this is, so there's sort of maybe 2 main factors. The voltage, the open circuit voltage of the isolated conductor, that's a function of not the length of the line, but some other factors. So that's a function of the operating voltage of the energized line. It's a function of the distance between the 2 lines and some other factors, like Darcy mentioned, the effect of hours. So that's the open circuit voltage. And that does not depend on how long ago you removed the earths. So that open circuit voltage will appear within a cycle, so pretty much immediately. And then the other factor is, then the other question is how much shock current is going to flow if you accidentally contact the line a moment after you've removed the earth. And that, again, that doesn't depend on how long ago you removed the conductors. That depends on some of the same factors, plus also the length of the line. And so if you have a very long line, then those with those capacitances, the capacitance will be high, and then the reactance of those capacitors will be lower, and you'll get a higher charging current, which will flow through the worker if they touch it after they've removed the earths. And again, that doesn't depend on how long ago you removed the earths. That hazard is there, will appear immediately. So I know that's a long answer. Does that address your question, Mark?
You bet. That was great. I think I can actually follow most of that too.
Okay,
So,
yeah, it is
thank you
very
very much.
abstract. Okay, yeah, I'm really glad you asked. I'll make sure to talk about it again in part 2, so we can use it as a separate video. Any other things you want me to come back over? Okay, time for a break then?
Does the earthing of the tower affect that, like the reference point for the 0 volts, or is that not? Does that not come into it?
So
the metallic tower structure.
yeah, you're saying does that affect the
Yeah.
electric potential in free space?
Well, because no.
Yeah, if the tower was bonded to Earth electrically and
Yeah,
is
that's what I
itself
mean.
bolted and connected, so it is. So the top of the tower is at the same potential as Earth, barring any small local variations and effects of the electric field. But does the earthing, the fact the tower is metal and earthed, assuming it is, have an effect on what you're explaining?
Yes, that does have an effect, and in this highly simplified model for the illustration, I've neglected that effect here. And so I'm saying that the towers are far off in the distance. We've taken a cut of the conductors in mid-span.
Okay.
And so that's part of the way that I'm neglecting the effect of the towers. But you're right, the towers do affect the electric field, and I have neglected that effect for the purpose of this illustration.
Yeah, okay, cool.
And that's a valid neglection, as in other words, it's pretty minor, it's negligible? Or is it?
I don't know how large the effect is quantitatively, but this is only for the purpose of illustrating the concept.
Right, okay.
So if you want to see it quantitatively, in my references, there's an IEEE paper, and they've used a different software package with a different model to model it accurately, much more accurately than I've done here.
Right.
Okay, is that okay?
Yeah, cool.
Edward, I had a question on the earlier slide. You showed the relationship between the 2 plates of the capacitor with a mid span or mid section and you drew that relationship as entirely linear. But then when we look at the field strength, so the voltage per unit of measurement or distance. So you said that the potential across that mid plate would be 50 volts if it's in the middle. But then when we look at the field strength, then the field strength isn't entirely linear with respect to distance between 2 conductors, is it? So you have a much higher strength closer to the conductor, obviously, and it's not a linear decay to Earth.
That's true.
And yeah, so I got a little bit confused here with that plate. Actually, if you were to put a multimeter on that with respect to Earth, would you measure 50 volts on that middle plate?
So in this case, regarding the 50 volts, yes, if everything's perfectly symmetrical, yes, you get the 50 volts. Regarding the shape of the field, yes, I 100% agree. Exactly like Darcy's point and Mark's point earlier, I have made simplifications here. So those field lines in the grey, that's the electric field, those arrows, those don't perfectly represent what the electric field will be in reality, because in reality it won't be perfectly uniform. And that does mean that the plot of the electric potential from one plate to another won't be a perfectly straight line. And So that's a simplification that I've made for the illustration. Yeah, so does that?
Yes, I think it does. Thank you. Yep. In my head, I guess I'm thinking if there was a presence of an earth path, if you had a low resistance, and you obviously couldn't sustain 50 volts on that mid plate, but in terms of it as when it's floating midway through the charge, then it would be at half the voltage. That's correct.
Yeah. So we've got a uniform insulating medium between all three of those. Okay.
Yep, I think I'm following. Thank you.
I'm glad you raised these points because they are all valid. Yeah, so I could have plotted it with this software, and then you would have seen that it wasn't all as simple as I made out.